we've got team pictures after school. I have to get ready and various things. But yeah, I'll be around.
Okay.
All right, let's get your homework out here and talk about the quiz for Monday. Now, get that assignment. Take out your assignment sheet also, the chapter 2 assignment sheet. Let's take a look at that. All right, so today the plan is to I've picked out some of the homework problems. I really think today's homework really was a pretty good synopsis of of a lot of things that are on, that you have to be able to do for the quiz. It's all pretty much in there. But you need, it's not just about what's going to be on the quiz. I know that's important to you, but there's a lot of concepts, a lot of things we have to be able to do and should be able to do, even though it may not be on the quiz, or it may not be as tough or whatever, as involved as something like number 48 maybe all the way through, but you've got to understand those things. So up here, so if you look at that assignment sheet, so we had those group of 3, 2, 5, 2, 6, 2, 7, and then if you look at the last group of 3 problems, that would be, I guess, your assignment for Monday, although obviously with the quiz Monday, we're not going to be going over them. Most of those are just kind of another attempt at the things that, you've been doing on the last couple assignments. So it's more review problems. And then there's that line that says review. Now, those are just problems I picked out that cover the whole chapter. Okay, so there's some limit problems, things like that. Well, those aren't really things that are on the quiz. So I've pulled out the ones that might be more related to things that are on the quiz. So if you wanted to write those down. So 3, 4, 23 through 29, that kind of stuff. Okay, so if you want to jot those down on that on your assignment sheet, that might not be a bad idea. And then also remember 2.4. We haven't done much in 2.4 for a number of days, but 2.4 was just where we first learned the idea of the number line, making the number lines on F and F prime, or F prime and F double prime, where we learned the idea of global max min, doing the list of candidates. But the difference is in 2.4 we did it with polynomial functions, so they were a little easier to solve. We factored and solved more easily there. When we get into section 2.6, we do the same thing with exponential and log functions. We get into 7, we do the same thing with sine and cosine functions. Okay, so 2.4, 2.6, 2.7 are really the same, really kind of the same topics. Now, with exponentials and logs especially, we got into some differential equations too, which of course is what we did in section 5. So there were some of those things. So what I put here is, in class we did 19 and 23 as part of our homework, I think, or in class or whatever on section 2.4. Some polynomial, local maximum, global maximum stuff. So doing number 20 and number 24 out of those sections might be good review too. It's just to review some of the polynomials. Okay? So what I thought we would do here is I've kind of organized some of the homework questions just to go over. So as we go through them, you might want to jot some things down, whether it's in your notes or just in your homework paper, whatever. But just to try to put it into an order that helps make sense of it a little bit. Okay. Now, as we go through this, there's obviously going to be people at different places as far as your preparedness for the quiz on Monday, my guess. Okay, there might be some of you are like, okay, I pretty much got this, and if I just go over a few things today, you're good. Okay? And if that's the case, as we're going through some of these things, and you want to start getting started on this other homework and these other review problems, feel free. Okay, that's fine. Won't bother me a bit. But I think there's other people that aren't at that spot. Okay, and so we'll spend some time going over these. And I say that because there's a number of people who, I'd volunteer.
Yeah.
To come up here Sunday at 4 if you would like some more review, okay, or some more help, or for me to work through some problems, or whatever the case may be. So Sunday at 4 o'clock, I will be up there. Now, I made that offer, and I talked about second block, and after we were done second block, I think there were still people who wanted to come up Sunday at 4, so I'll probably go be. Nobody shows up. A lot of that crew, I think, still here. I think there were a few that said, oh, you know, it kind of made sense after the day, it may not come up. But after working through some of these, they may change their mind too. So whatever. Okay, so that offer's there. So I'll be up here at 4 in this room. Probably the weight room door back there will be open, or propped open or something. So anyway, if somebody wants to take advantage of that, you can. Okay, will I record the Sunday thing?
Yeah.
I don't know. I put it. I don't plan. I'm not going to have a formal presentation. I'm going to be here and say, "What do you got questions?" So I'll just help people. You know what I mean? I'll just help. But listen. There's all kinds of. There's a recording of today's. I'm recording today's, and there's all those videos of all the global maximum solving an issue about a problem. All those little 5-10 minute things are up there. So there's tons of things. Okay, that are available. All right, so let's start with this. So we talk about differential equations. That's probably a good thing to focus on first. This idea of differential equations is the most new and it's the most sometimes confusing thing. And so there are a variety of things we talked about being able to do with differential equations. The first one I want to talk about is this idea of the 3 different types, because that seems to be confusing some people here when you actually start to work. There's a type where we can do the actual antiderivative, and what that means is, well, back up. Understand the solution to a differential equation is the original equation y. Okay, y equals with a bunch of x's in the input variable. Okay, you got to understand that. All right, and so if I have a differential equation that just has x's or t's in it, whatever the input variable is, or a constant, I can just do an antiderivative, and that'll get me the original equation y, and that's my solution. That's one type. Another type has to look like this: y prime equals ky, not ky squared, or not ky to the 1/2, or not. It's got to be y prime equals ky. If that's the case, then the solution, the original equation, is y equals ae to the kt. Okay, and if it's not one of those two types, if it's got x's and y's and y primes and a mixture of all those things, if it's not one of these two types, then it's this type. We don't know how to solve it. And the only way we can know the original equation y is if they tell it to us. Okay? And then we could verify that it's a solution, but that's the only way we would know. Okay, so it's important you understand those 3. So now if I take our homework problems, and they weren't really in this order, but if I put them in this order, I think maybe it'll help you see that. So here's number 9 on, what was this, 2.5, I think. Okay? So, this is which type? This is the first one. Now, we have this idea of IVP, initial value problem. What's that mean? Well, yeah, but I mean, that's how you work it. But what's an IVP, initial value problem? It's a differential equation. Well, it's an initial condition. That initial condition helps you find the C value, right? But an initial value problem, an IVP, is just the same as a differential equation. It just has the added thing of having an initial condition. So it's like in chapter 1 when we had an F prime graph, we want to find the F graph. We were really getting the solution to a differential equation when we did that, graphically, okay? But there was an infinite number of them. But if they gave me a starting point, then there was only one of them. So on all these problems where it says how many solutions are there, that's like it's either infinite or it's 1. If they give you an initial condition, there's one solution. If you don't have an initial condition, then there's an infinite because we don't know what C is. Okay? So when it says solve a DE, that's the same thing as solve an IVP for the most part. It means find the original equation. The only difference is in an IVP, you have this initial condition that you can stick in there. So on this one, they said solve this IVP. So this is type 1, right? This has x's in it. We can just do the antiderivative. So we do that. Now, if we did not have an initial condition here, right? If this initial condition was not given to us, then we'd be done. That is the solution to the differential equation. How many are there? An infinite, because we don't know what C is. But since they gave us the initial condition, we move on and we put the 1 in where the x is, and we put a 2 where the y is. So it looks like that. And then we work it out, and we find what C is. And many people mistakenly think they're done at this point because it feels like you're done. In algebra, when you get C equals -6, you're done a lot of times. We're not done. What do? Plug it back into the y. The solution we're looking for is the y equals the original equation, which is this. Now, this has a name. This is called the general solution to the differential equation. There's an infinite number of those solutions because we don't know what C is. This is called the specific or the unique solution to this particular initial value problem. It's the one that is the solution for that initial condition, for that starting point. Okay? So very important to understand those basics of the differential equation. If you don't have those, then yeah, these get very confusing. You just don't know what to plug where and what it means or anything. Okay, so that is the key. So this was a type 1 where we can do the antiderivative to solve. And not only that, but that gives us practice at this part of the quiz too. Right? In this part of the quiz where I just want you to do a derivative or an antiderivative. It's possible that I may give you a problem on the quiz where I just give you, I just give you this and say find the antiderivative. Find y. And then you just do this and you'd be done. Now, essentially, you were solving it as solving a differential equation, but that might not even be the directions. The directions might say, here's y prime, find y. Or it might be, here's f, find big F. Or just say, find the general antiderivative, right? And that just means put a plus C in. Okay, so then we go on to 13 in section 2.6. So now I jump to another section here now. So I don't know if it's out of order in your homework here, probably. Okay? But now, here's a differential equation. Actually, it's an IVP. It's got an initial condition limit. Which type is this one? See, I think a lot of you, when you looked at problem 13, didn't recognize this. This is the second type. This is y prime equals ky. So we don't know how to solve it with an antiderivative. We just memorize that that is the solution. So when you see y prime equals 3y, you need to be able to just go to that next line. You just need to know that, hey, oh, that's that one that has y equals 8 e to the kt, and the k is 3, so we put a 3 in there. So if we were supposed to solve this differential equation, we'd be done. But they've given us an initial condition, so I put the 0 in for t and the 37 in for y. Now, I know some of you know that that 37 will end up just being the a, but think of the a as the plus c. The a is just the unknown constant. That means there's an infinite number of solutions here. Later, we'll learn how it was a plus c actually at one time, and it turned into the times a. We'll learn that later. Okay? But that's what that a is. It's just that constant that we don't know. So there's an infinite number of solutions. But now we put our 0 in for t, and we put our 37 there, and e to the 0 is 1, so that just means a is 37. So then we plug that back in for a, just like we plug the -6 back in for c. And there's our specific solution. So this is a general solution of the differential equation, and this is the specific solution to that IVP, the one that has the initial condition. Okay? So, same exact problem as whatever number the word 9 that we just did from section 2.5. Okay? And then we go to number 12. Now I'm jumping back here again. I'm jumping back to number 12 on 2.5. And this is very much like number 11 on 2.5. Okay? They give you this differential equation. And they give you this initial condition. Now, which type is this? Well, I've heard first. I've heard second. Anybody want to say third? Fourth. Third, fourth. Somebody here requested fourth. You like third. Why is it not the first? It's got y in it, not x. The first type has to just have x or t, the input variable. How do you know y? Why couldn't y be the input variable? Well, actually, it could be. Y could be the input variable. How do we know Y is not the input variable here? Because of the Y prime. We never put a prime on the input variable. The prime is always on the output variable, F prime, right? So we know Y is the output variable here because of the Y prime. So you cannot, type 1, where you do an antiderivative, you can only do if it's the input variable in the problem. So this is not type 1. Why is it not type 2?
Because you can't.
Because this is Y to the negative 1, right? Type 2 is Y prime equals K times Y to the first power, like the one we just had. Y prime equals 3Y. That's the Y equals AE to the KT one. So this is not either one of those, so it's got to be type 3. Type 3 is all the rest, the ones we don't know how to solve. So if you don't know how to solve it, you have to be given the solution. And I would suggest to you on 12 we were given the solution. Back in problem number 6 that we did yesterday. Okay? Back in problem number 6, they said the solution to this differential equation was this. Remember, this is the one when we verified it. Remember in 6, we verified it. We forgot to kick out the negative 1. Remember that? Right? That was this one. Okay? So now I'm not going to be that kind of vague on the quiz. On the quiz, if I give you this differential equation and it's a type 3 where we don't know the solution, I'll just tell you the solution. You know, verify that this is the solution. I'll just say, hey, this is the solution to this differential equation. Now solve the initial value problem, which basically at that point would just mean put in your initial condition, right? So this is the general solution that has infinite number of solutions. And then we plug in our 0 for x and our 2 for y. And we figure out what c. So what would we do here to solve this? Square both sides. C would equal 4. And then you plug the 4 back in where the c goes. So see how those were all kind of the same problem? Solving the IVP. Now, if you did not have an initial condition, then in every one of those problems, we would have stopped right there, right? That would have been our solution, right? Because we didn't have an initial condition, so we had an infinite number of solutions. It's our general solution. But if we have an initial condition, we plug it in, we figure out what the unknown constant is, either a C or an A or whatever, and then we plug it back in, and again, our solution, our final solution is always the original equation y. Y equals with x's in it, like that. Now, the hope is, like on problem 48, like a story problem, that we would then be able to work with it, right? Because now I might ask you, well, what's y of 7? Or when does y equal 7? So y of 7, you know, if I said, now, solve this IVP and find y of 7, what would you do? You just get down to the bottom here, plug in a 7, you get square root of negative, oh, that'd be under 5, okay, but anyway. Or if I said, when does y equal 7, you do what? Put a 7 there and square both sides and solve for the x, right? So once we have that solution, we can then use it and work with it like we normally would any other equation. We could answer questions about it, okay? Natalia, what was your question? Okay. All right. So now, just as another one to do on that same section, number 10. Now, number 10 is the same thing. It's a differential equation with an initial condition, so it's an initial value problem. They want us to solve it. Now, what type is it? This is the first type because it's got all x's in it. The only thing hard about this one is that the antiderivative is a little tougher, right? Back here, that was a pretty easy antiderivative, right? So that made that problem easier, assuming we knew what we were doing as far as the whole solving and finding C in that. Okay? But now, number 10 is just harder because it's a harder antiderivative. But let's just run through it. So this is good practice. This is good practice for this part of the quiz right here, where we have to be able to do derivatives and be able to do antiderivatives. Okay? All right. So, what's the antiderivative of 3e to the x? Yeah, e to the x is its own antiderivative. What about 3 to the x? Well, 3 to the x is kind of its own antiderivative, except what? Yeah, well, there's gonna be this ln3. Now, the derivative rule, I remember, the derivative rule says 3 to the x will be 3 to the x ln3. So whatever I put here, if it was just 3 to the x, when I do the derivative of it, would have an ln3 there, and I don't. So I need a 1 over ln3. Now, some of you said 3 to the x over ln3, which is fine. I just think division is more confusing in calculus as we go through the year than fractions are. I'd rather have, in other words, instead of x over 7, when we do derivatives and stuff, it's just a lot easier to think of that as 1/7 x. It's just easier to think of it as a fraction in front than dividing. So that's why you see me write it this way. What's the antiderivative of 1? Antiderivative of 1. X. And then plus c. All right? So the antiderivative ends up being that. Okay? Now I'm probably not going to ask you one like that in the midst of a differential equation type problem. But I might ask it to you on a problem where all I wanted was the antiderivative. You know, all I wanted was that, and you were done. Okay, so that ln3 thing. Now remember, that's nothing different than this one. If I have x to the 4th and I want to do the antiderivative of that, you know it's got to be x to the 5th, because if the power's got to go up 1. But it can't be x to the 5th, because when you bring the 5 down in front, you would get 5x to the 4th. Well, yeah, there's no 5 there, so there must have been a 1/5 there that canceled it out when we brought the 5 down. Well, the same thing's true here. When you do the derivative of 3 to the x, you know you're going to tack on an ln3. So there must have been a 1 over ln3 there to make it go away. So that's the thought process. Okay, I know it is easy to confuse derivative rule versus antiderivative. Just remember, we have derivative rules. With antiderivative, just kind of guess and check with thinking of the rules back. All right, so now what do we do next? Right? Now we've got, just like there. Yep, I did the same thing. So set it equal to 0. No. This is an initial value problem. That's our general solution. We take and put zeros for the x's and 0 for the y. Now this one gets kind of messy too, and if you had to do something like this, it'd be more like on the calculator problem. Not that we can't do it, but I just don't want to get all bogged down on the quiz in some of these things. We got enough stuff to do on this quiz. Okay? But we still should be able to do this. So we put a 0 in for x, so we have e to the 0, put a 0 in for that x, put a 0 in for that x. Now e to the 0 is 1, so that'd be 3. 3 to the 0 is 1, so that'd be 1 over ln3. So we end up with that. So then how do we solve for c? Yeah, just move them over, right? Just subtract the 3 over, add the 1 over ln3, that's just a fraction, just a number. So c ends up being that thing. No problem, just take that then and put it right up here where that c is. So just look like that. Okay. So you don't have to know what ln3 is. And that would be fine. If this was a calculator problem, go ahead and put it in. Just make sure you use through this. All right. So that's this whole, really probably the new thing yesterday was this idea, one of the new things was this idea of IVP, initial condition, and just make sure you understand. Hopefully this clarifies that a little bit for you as far as the solution to a differential equation, the original equation y. If you have an initial condition, you put that in, that gets the c, but again, your answer is still the original equation. All right, so with that in mind, don't look. Try that one. Here's an IVP. It's a differential equation with an initial condition. Solve the IVP. Solve the IVP. All right, so first step, which type is this? This is one we can do, we can solve it, we can do the antiderivative. So is that what your antiderivative looks like? Negative cosine would be the antiderivative. Sine, 1/3 x cubed plus c. Put in our initial condition, put our zeros in. For the x's, cosine of 0, of course, is 1. It'd be -1, this would all be 0. So c would be 3. So we put the 3 back in. So our solution to the initial value problem is that. Again, I still think it's hard to get out of your head when the problem says solve the IVP, you want this answer like 2 or something. That down there is the solution to the initial value problem. The original equation 1. All right. And that brings us to number 48. So, that is on page 131. Let everybody open up to page 131 if you would. And the other things that you need to know about differential equations are all in this problem. Okay? We need to know the different types of differential equations. We need to know what it means to solve a differential equation. Either you can solve it or you're just given the solution or you've memorized it's that y equals a kt. Once you have the solution, you need to be able to put in an initial condition to get the c or the unknown constant. And then the thing we haven't done yet is this verify a solution. We've done it, but not today. Verify something's a solution, use it, whatever. If you can do those things with differential equations, you're in great shape. I guess the other one, and this is what I want to do right now, is that interpret. Yesterday we talked about interpreting, we talked about proportional to, right? Put a K in there, that thing. So here's what I want you to do. I want you to read the first sentence there on page 131. Read the first sentence right up until it talks about Torricelli's law. 48, page 131. All right, now, I want you to read it again with these directions because this could be, that first sentence could be a problem on the quiz where I say this. For the following situation, let y be the depth of the liquid. Write the differential equation that describes this situation. Okay, so read it again and see if you can do that. Write the differential equation where y is the depth of the liquid that is described by this situation. All right, well, if you're going to get it, I would guess you already have it. So, I told you y is the depth of the liquid. The sentence says that when the valve at the bottom of a tank is open, the depth of liquid in the tank drops at a rate proportional to the square root of the depth of the liquid. So what's the rate? Y prime. That's the rate that the water level drops. Then what? Equals proportional to, no, times the square root. It says the square root of the depth of the liquid. What was the depth of the liquid? Y. I told you y was the depth of the liquid. So it's y. If it's square root of the time, then it would be t. Right? T is the time, y is the depth of the liquid. So I would want you to be able to write this very simply. That'd be like 1 point, maybe 2 points. 2-point problem, whatever. Just do that, right? Now, later on, it tells you that, right? Now, mine's different, though, than the one they give you, isn't it?
Yeah.
Why? They put a negative on front. We're going to talk about that in a minute. But this would be okay. This would be okay. This would be good enough. Okay? So, I mean, it's simple, though, isn't it? I mean, the sentence said all that. It said the rate that the depth changes, that's y prime, is proportional to, we talked about that, that's where you tack on a k, right, times. And it says the square root of the depth, and the depth is y. I mean, it's just all right there. You just translate the words into those symbols. Okay. So that's a difference equation. Remember what I said about differential equations? They pretty easily model real-life situations like this. They're just not very good at helping us find out information about that situation. Like, this is terrible at telling me how full the tank is in 2 minutes or in 20 minutes because I have nowhere to plug in a 20 at time. Okay? And it's got the rate in there. So it's terrible for that. But the solution isn't. All right, so let's just stop a minute and think about this situation. So pretend you have one of these big blue water jugs, right, with the valve here at the bottom. That's what we're talking about, right? And whenever you have a proportionality thing like this, what you're saying is that this side gets bigger as this side gets bigger, right? And as this side is smaller, this side is smaller by this certain amount, whatever K is. So Y is the depth of the liquid, right? So the bigger Y is, so the more liquid we have, the bigger Y prime is. And what's Y prime? The rate what? That it's draining out. So you ever had one of those big water jugs, right? And it's full, and you hit the spout, what happens? Comes out pretty fast. Then when it's barely full, comes out a lot slower, right? It has to do probably with gravity and the pressure and all those kinds of chemistry, physics kinds of things, right? So this makes sense, though, right? That there's some connection there between the fuller it is, the faster it comes out. And this describes that situation. Okay, now let's talk about K being negative, because this could be something else I could ask you. I could give you this differential equation, describe the situation to you like we just did, and ask you, is K in this, look at mine up here now. In mine up here, is K positive or negative?
Doesn't say.
No, now listen. In the situation that we just read, don't look at the rest of the problem. In the situation I just read, and for this differential equation, is K positive or negative? Negative. Sam, why?
Because the water's draining out, so the water is getting less and less.
Well, okay, I do agree with you. Everything you said is good, but you need to be more specific. I would like you to be specific about these actual values here.
So like talking about how the rate would be getting less as well.
No, not quite that. Somebody add on to what he's saying. Yeah, I can tell by what you're saying you know what's going on.
It has to be negative because the slope of y is negative. So y
Okay? And in this case, I'm not sure the word slope helps me too much because that's more the mathematical thing. But yes, you're right. What you said is true. Let's go to the chart. What is y again? The depth of the liquid, right? So is y positive or negative? So y is positive. And the square root of that is definitely positive, right? So what I would like to see is you explain that, okay, square root of y has to be positive because it's the depth of the liquid, okay? And then what's y prime? Okay, now let's go to the chart now again. What's y? What's happening with y in this problem? We said it's positive, yes. It's decreasing, right? That's less positive, that's true. Isn't y decreasing? Right? That's the depth of the liquid is decreasing. Think of the chart. If y is decreasing, that's what I'd want to hear, right? Y prime is negative because, so in your explanation, Sam, your explanation was more about how come y prime is negative, not why k is negative. You see the difference? Okay? So because the water level is getting less, y prime has to be negative, okay? So in this problem, y prime has to be negative, this has to be positive. For that to work, what's k got to be? K's got to be negative. Okay, now if you look in their problem, what did they say k was? No,
They said K was positive.
they say k is positive. Well, that's because what did they do?
Put a negative.
when they wrote their equation, they stuck a negative right there. Well, again, so if I gave you this and said, what's K? And this is where your explanation wouldn't work, right? You see what I'm saying? Because here K is positive. Well, how come? Well, we go through it again. We know Y prime has to be negative because Y is decreasing. We know Y has to be positive, and we know we've got this negative here. So what's K got to be? K's got to be positive to make both sides be negative, right? So they just stuck a negative on, I think, just to help emphasize the fact that, yes, Y prime is negative, so this side over here should be negative. So by having a negative on there, it makes it feel like, oh, yeah, okay, we're working with a negative. But I wouldn't have had to put the negative there. I could have had K be a negative constant, all right? But in theirs, it's going to be positive. All right, very good. But understand now, that's important to keep track of later on, that Y prime is negative here because the water level is dropping. See, the chart is good and everything, but you sure got to be able to pull from it and use it in problems like this. Because really, all this stuff we're learning, this is a problem why we'd want to have this stuff. I mean, this is a situation where all this becomes valuable. We can't do it in problem 38, then why have any of it anyway? All right? Even then, it might be questionable. All right. No, that's not true. So number one, we've kind of, or part A, we've kind of answered, right? It's going to be coming out faster when it's full rather than half full. So we kind of answered that. All right, then we go to part B. And is that where they give us the proposed solution? Isn't that where they tell us that? Now, again, remember what I said about division? I don't like division. I'd rather work with fractions. You know, they have that over 4. I would write this way. To me, this makes more sense. So if I was writing that problem, just from my experience in calculus and what we have to do later on this year, if I were you, I would get used to start writing things this way instead of over 4. To me, that just makes things more confusing. So that's their proposed solution. Because clearly, shoot. Which type of differential equation is this? It's the third. It almost looks like the second, but it's got square root on it. And that's, the second has got to be Y prime equals KY. That's it. Okay? All right. So, okay. So they just have to tell us the solution. And so they have. Now, is this where they tell us to verify? In part B? Verify. Okay, so let me move to another page. Now, which one, because people always get confused on where the T chart goes. You know, where do I put the T chart? So I'm going to do a verify, which means I'm going to have a T chart. What's going to go up on this T chart? Which one of these? The Y prime one, right? It's always the proposed solution that we plug into the differential equation. So I'm going to come over here and I'm going to have Y prime equals negative K square root of Y. And I'm going to take my proposed solution, this, and I'm going to put that in to this. So I got negative K and then square root of all that. So this is good practice on this verify part. This could be just one question on the quiz right here. Here's a differential equation. Here's a proposed solution. Is it a solution? Verified. Okay? So how do I get Y prime over here? Do the derivative of this. So what would that be? I'd bring the 2 down in front. It would be 1/2. What do I do with the inside? Leave the inside alone. And that would drop to the first power, and we have a negative. Remember, now the T is the input variable here, right? T is like the X. So whenever you have something multiplied by the X, or in this case multiplied by the T, we have to kick that out. And so we have to kick out a negative K. Now that, and multiply by it. So I can bring that around in front, and so that would be negative 1/2 K times a quantity C minus KT. Now, are those two the same? Not yet, but I think we can. Now, what I have is a 1/4 times something squared. Now, this is a little property of square roots we got to talk about. Now, we've already talked about how we can't do this one, right? We can't do this. That's bad, because this would be square root of 13. Square root of 13 is not 5, right? So that's no good. But what if you had 4 times 9? Is that 2 times 3? Yeah, because square root of 36 is 6, and 2 times 3 is 6. So we can do that. So we can do the square root of 4 and the square root of the 9. So here I can do the square root of the 1/4, which would be 1/2, and I can do the square root of that squared, which would be c minus kt. And I'd say that's close enough if you got to that. So those are the same. Okay? So that's verify a solution. So one more chance to practice that. All right? Now, also in that, was that in that part where they said c minus kt has to be positive? They said for this will come in handy here in a minute. They said for physical reasons, c minus kt has to be positive or 0. Now, the reason for that is because, again, we said that y prime has to be negative. Remember that? Remember that? We just found out y prime's got to be negative in this problem. Well, look. K we said is positive, right? So this would be negative 1/2. That's negative. And for y prime to be negative, what's c minus kt have to be? Right? I wrote it over here. Okay, right here. This is y prime. This has to be negative. K is positive. We already established that. So this out here is negative. So for this whole thing to be negative, c minus kt's got to be positive, right? So everybody okay with that? So they gave us that. Now I'll show you where that's going to come in here in a minute. Okay, let's go back to C. So part C says what? Oh, right. Okay. So it was nice of them to tell us this. In function notation, that made it easier. They said y of 0 is 9 and y of 20 is 4. What did they just tell us there? What did they just give us? Right, but those are initial conditions, right? They just turned this into an IVP. Because actually, in this case, we've got 2 unknowns. We've got K and C, right? 2 constants we don't know. If you've got 2 constants you don't know, you need 2 initial conditions to help you. So we need to know not only how much our starting point was, how much water do we have at the start, but we need to know something about how fast it's draining. That's what the K is. Something about how fast it's draining. So we need to see at 20 minutes it's down to 4. So that with those 2 pieces of information, we can find both C and K. We got to just plug them in there. Now I might not have written them for you in function notation. It might have just been in the sentence. It might have said the tank started with 9 feet of water, and 20 minutes later it was down to 4 feet. Right? So you would have to be able to pull that information out of the sentence and think of it as initial conditions. Okay, so make sure you could do that. All right, so now let's just do it. So let's take the 0. That's always a nice one to put in first, so let's do that. So we put a 9 there. Put a 1/4 c minus k times 0. Remember, we're putting it in for t. Okay, what do we get now? Well, no, not 1/2. We're not doing a derivative or anything. We're just solving it. And this would be c squared multiplied by 4. I mean, this probably would be a no calculator problem. I mean, really, the math or algebra on this is not that hard. Now, here's something we got to keep in mind. This really should be plus or minus 6 here. Okay? I mean, when we solve that equation, this should be plus or minus 6. Well, here's where that c minus kt thing being positive comes in. Okay? Because we know t is time here, and time is positive in this problem. And we know k is positive. So this is a positive value. If c is negative, you'd have negative minus a positive. What's that? Negative minus a positive. Wouldn't that always be negative? Like negative 4 minus 3, that's negative 7, right? Because minus a positive is like add a negative. So you have a negative plus a negative. So if c is negative, this thing is going to be negative, and that's no good. So we know we don't need the negative 6. Now on the quiz, we should be able to do that. And we're gonna have problems when we have to think about that consideration. On this quiz, that wouldn't come up, okay? So C is 6. So what do I do with that? Plug it in. So I got y equals 1/4 6 minus kt squared. Now what? Now take your other initial condition. So that found one of the constants for us. Now let's find the other. So we'll plug in a 4 for y. We'll plug in a 20. This one takes a little more work. Plug a 20 for t. That'd be 20k. All right, now this one's a little trickier. So what would I do first here algebraically? Multiply the 4 over would be a good plan. I really do not want to FOIL that out. That's not going to be very helpful. Square root both sides. Now, again, technically that should be plus or minus 4. However, isn't this thing right here the c minus kt? Right? This is c minus kt right here. And what do we say that has to be? Positive. So it can't equal -4. Okay? So again, that wouldn't come up on the quiz next time, but all right. So we subtract the 6, we get -2 equals -20. Okay, so k would be 1/10. And so finally take that and plug that back into there. So we get y equals 1/4 6 minus 1/10 t squared. That took a while. Now, we're still not done, actually. Yes. Now, it doesn't matter the order. However, 0 is always good because usually one of the constants goes away, especially if you have two constants. So using the 0 is better. If they would have said to us y of 10 is 9 and y of 20 is 4, what we'd ended up with is two equations that both have c and k in them, and we'd had to solve one and substitute. Remember, two equations, two unknowns in algebra? We'll get into some of those later on, but now it doesn't happen. So now, this solution, now remember what I was just saying with differential equations before. The whole point of solving that and finding that is that's more useful than the original function. This will tell us the depth of the liquid at any time. So now in part D, or whatever part we're on here, it says show that the tank is empty in 60 minutes. So what do? You put a 60 in for the time. 1/10 times 60 is 6. 6 minus 6 is 0. Y would be 0. The depth would be 0 at 60 minutes. Or they could have asked you, at what time is there 6 feet in the tank? Put a 6 in here for Y, and you would solve it for T. And that would be the time that there were 6 feet. So we could ask all these questions about what's going on with the tank at various times with this. Okay, last question then. It says, when is the water depth dropping at 0.1 feet per minute? That's when they want to know when y prime is 0.1. Well, we've got two different y primes. We have this one, and we have the one when we did our verify. Now, we already know C and K, right? We found those. Which one would you rather use to plug the 0.1 in? Simpler, but I would suggest probably, why this one? Well, yeah, but and we know K here. Okay, why would I rather have the one that has the T in it, not the Y? Well, what are they asking for? They want to know at what time is it dropping 0.1. So to me, you put the 0.1 here. Of course, this is 6, this is 1/10. Then you solve it for T. Now, you could use this other one. You could put the 0.1 here, and of course K is 1/10, and then that would be how deep the liquid is when it's dropping. Then you would have to come down here and put that in for Y and find out what time it was that deep. So you'd have to end up using two equations. It wouldn't matter, you could do it either way. Now, one thing nobody caught there, or at least you didn't speak up, it would be wrong to put 0.1 here for Y prime. It would be wrong to put 0.1 here Well, not really, really wrong, but just a little bit wrong. The water is dropping. What have we been saying this whole problem about Y prime? Y prime is negative. Y prime is negative because the water is decreasing. So when we plug a 0.1 here for Y prime, we really got to plug negative 0.1 for Y prime. So yeah, if you'd have plugged Y prime, if you'd have plugged the 0.1 in for Y prime, you would have got the wrong answer. Probably would have come up with a negative time, and then you just said, wait a minute, something's not right. Okay? Y prime is negative in this problem, so, and they said right there, it's dropping at a rate of 0.1 feet per minute. That's kind of like something moving left. It's got a negative velocity, right? If I'm going left at 50 miles an hour, my velocity is negative 50. Same thing here. Okay, so you plug that in. I think it comes out to be 40. I think it's at 40 minutes. So I'll leave that to you to plug in and try it. Okay, so I had a lot of stuff, but you know, you wouldn't have any one problem that would have those things, but you got to be able to verify difference equation, got to be able to use a solution, plug in an initial condition, do that, so forth, so on. Okay, all right, and now, all right, let's stand up and stretch for 45 seconds. All right, have a seat. Here we go. All right. Now, here's what I want to know what we need to do. What I have left on the plan is 41, which is the chart problem, no calculator. And then we've got 45, which was the calculator. Yesterday we went into some detail on how to use a calculator and that kind of stuff. So I would be glad to use our remaining time to go through this, because it's like half the quiz, right? I mean, chart stuff, how you write your answers, number lines, global max min, doing it on the calculator also, that's huge. So we have to be able to do that. So I'd be glad to go through another set of these just like we did yesterday. That'd be a good use of time. Like I said yesterday, or earlier this period, if you're saying, hey, I got that, no problem, and work on these review questions, that's fine. Okay? Read your English, whatever. Okay? No, because if you're coming Sunday, you have to read about English. If you're coming Sunday, you got to listen. Well, that's true. Not 41 and 45. Little bit of 40.
She can come up
You're
there.
right. A little bit of 40.
Yeah.
John,
Let's
what's
try
that?
I think what time we're in?
I'm going to be here at 4 o'clock p.m. Absolutely. And I will stick around for whenever.
Is this Central Time, Pacific Time,
Central
Eastern Standard?
Standard Time. Are we in Standard?
I think we're in Central.
All right. Well, I only say that, Brittany, because somebody in the other class said, oh, let's just sleep for the last half hour or something like that. And then I got mad, and I said, if I'm giving up my Sunday, if I'm coming up here on Sunday, you're not going to spend the next hour asleep.
I have a question about.
Trust me,
I have a question about.
that's my wife.
The collapse of Q1 in 1999. You still have it? I saw a great picture of you.
Where did you see a picture of me from 1989?
Oh, you're falling down like 50 euros or something.
I do not, I might have those glasses. What were they, big?
Oh, they're monsters.
Big. I had the big, yep, had the big, I had the plastic lenses, I had some, then I had the little ones, I had the little one, those were kind of in style.
They got contacts.
Well, actually, they were in style, I probably had the big ones, then as they went out of style, I probably got them. But I'm typically a little behind on the style. I think that's because my wife is the one that gives me style. Would that, don't you agree though, probably, right?
Is
I
that this
mean,
recording?
neither one of us, it is recording once again. My, no, that's, I guess, why we're married, because neither one of us are care too much about that. Neither of us care too much about that. But anyway, but then I had laser surgery about 5 years ago. Man, that was awesome. That was the best I did.
I think I'm gonna get that.
Best thing yet. Now it's about 5 years ago. It's starting to
It's gonna get
little
fuzzy.
blurry, little bit. Not
I'd rather have that than my eyes.
Yeah,
Yeah.
it's not
I
bad.
hate
It's,
the contacts.
So about how much did it cost?
I think at the time I did it, I think it was about $1,600 per eye.
So times that by 10. That's
So,
what
yeah.
it'll be today.
So no, I don't think it's a whole lot.
Wow, that's
Sometimes
not
those
much-
things actually go down.
that's
Now
not
mine
as much
was
as I thought it was.
they've changed it a little bit now. It's changed over the years. About 10 years ago, 10 or maybe a little more than that. They used to, none of it was done with a laser. It was all with
Yeah,
a little
my
knife.
mom
They
had
actually
it with a
cut.
knife.
They put
Yeah.
your eye.
And you're awake and you're watching it.
No.
It-
And-
Oh.
It's like cut off.
Well,
They cut off layers.
right. Well, but then,
Flip it back.
but-
Yeah, it's
okay, they first have to cut the layer over your eye and flip that back, because what they do is they reshape your eye so it reflects the light on the back of your eye where it's supposed to hit instead of shorter there.
I
which
wouldn't
is
trust
like
someone's hand to shape because of
well,
little-
that's what surgeons do. And so, but then when they introduced the laser part, what the laser does or did then was reshape your eye so that it would focus right. But they still, when I had it done 5, 6, 7 years ago, they would just start to change that. They still had to go in with the little knife and cut the flap, and then they fold that back. Then the laser came in and reshaped, and that was all computerized. They'd already mapped out your eye and everything. And then that was computerized, and then that reshapes the lens, and then they fold that back over. So then for multiple weeks after that, I had to wear these sunglasses so I wouldn't rub my eye because I had to heal back up. You know, that had to heal back up. The flap. The flap.
How does it go back?
Yeah. What's
How
that?
does it like stay there?
Well, and once they fold it back up, I think it just grows back together, kind of
Oh,
like your
no,
skin if
no.
you get cut.
Well, yeah, but like what if
No, yeah, if you blink, that doesn't bother you. You'd have to rub it pretty hard.
So did you like watch him do it?
Well, I mean, what happens is number one, they kind of give you some sedation, you know, so you're awake,
So
but
you're
you're
like,
kind of like, you're kind of like, and
But
then
they don't knock
they've
you
got
out?
these clamps. I mean, they don't knock you out. They've got these clamps that hold your eye up. But you're there, and this machine, I mean, it comes right down. I mean, so you can't blink or anything. You can't really. I mean, you kind of hear this, but you can't tell. It's just kind of this bright light. And you're just kind of sitting still.
Did your a
It's
bright
not
like
bad.
no blinking, eyes watering?
Yeah, I mean, they've got this
Yeah,
thing
you wouldn't realize
clamped
that.
open. You can't blink. I mean, you can't really screw it.
I watched them do it.
Yeah.
It's like it's hilarious. She's like almost under the face.
Oh, really? It's done in minutes. I mean,
And you
it
do
doesn't
one
take long.
eye at a time,
No, they did
different.
both eyes. They did that one, well, one at a time, but then they moved it over. But now they use a laser to cut the flap and everything. So they use a laser to cut the flap open, and then they do the laser to do the thing. So it was blurry for a few days, but it after about 2 days it was pretty good. The technology's better, and so but it's I think it's still pretty much the same price. It's pretty similar. But it's, now you guys are a little young because, you know, your eyes are still changing. Usually they want you to wait till 20 or in your 20s a little bit. Because your eye, the shape of your eye is still changing a little bit. And so if they do that and it changes after that, then you'd still be blurry.
Well, my eyes are graciously for a year.
Oh, mine was pretty bad, like -5 or so.
That's not bad.
Well, that's not horrible.
Mine
My
was
glasses
7,
were like
Riley's
real.
a 9.
Oh, okay. No, mine was like 5 or 6.
Mine are terrible.
All right. So anyway,
Back on
let's, back on the, so how do we get on there? Oh, he's asking. Okay, so number 41, now remember, if it's a no calculator problem, I think I might still have it. On 41, if it's gonna be a no calculator, it's gonna have stuff, especially the trig. Remember, 2.4, this is what I said earlier, 2.4, number 20, 24, those are some polynomial ones with max and min, where you just do some factoring, you know, and the algebra is simple. So we go ahead and do the derivative. All right, now some people that came in this morning didn't realize that x is not under that square root. So the square root of 3 is just a number out in front of the x, like a 7x. So when you do the derivative of square root of 3 times x, it's just square root of 3. So you do the derivative, you set it equal to 0, you add that over, divide, you get root 3 over 2. Use your unit circle, you got cast, right, all this stuff. So cosine first, fourth quadrants. Root 3 over 2 is, if you draw your triangles, root 3 over 2, 1, this would be 1/2, so this would be 30 right here. So that'd be pi 6. So we're looking at pi 6 and 11 pi 6. Okay, is our stationary. Now, this is one of those problems that wanted everything. I mean, a global, I'm not going to ask you for all that stuff. I might just say, here's a function, where's it increasing, where's it concave up, does it have a local maximum, or something like that. Well, if I ask you for increasing, decreasing, local max, local min, that's F prime, right? Inflection point, concave up, concave down, F double prime, right? So, and then global max min is endpoints and stationary points, which means you need F prime and the endpoint, right? So so this problem has it all. You wouldn't have to do all this in any one problem. So if it's global max min, we've got enough information, right? We're already ready to do our list of candidates. We've got our 2 stationary points. We've got our endpoint 0, 2 pi. That should be G there, absolutely. And so we would come over here and we would plug 0, 2 pi, pi 6, 11 pi 6. And we would put those into the original G function and find those values. Now, this gets messy with the square root of 3. I wouldn't have you do that on this quiz, okay? It's really not beyond what we eventually will be able to do or might be asked to do on the final or the midterm or something like that. But for this right now, it would be simpler plugging in, or else this would be on the calculator side. But so anyway, you can just plug those into G, use your calculator, that'll be fine. Get those values. There's your max of your unit. All right, so let's say we were just doing a chart problem then. So let's say we're doing local max and that kind of thing. So we would take our stationary points, put them on here. I don't like to use the endpoints if I don't have to, but in this case we kind of have to. So we're going to plug some numbers in to G prime. All right, whenever you do a number line, you're either doing a G prime number line or a G double prime. So you're plugging those values always into G prime and G double. So we take 0, and here's our G prime. So what's cosine of 0? Cosine of 0 is 1 times 2, so that's 2 minus root 3 positive, right? Because root 3 is less than 2. Root 4 would be 2. So root 3 has got to be less than 2. It's about 1.7, but for sure it's less than 2. So 2 minus that would be pi. And then we put pi in our cosine of pi. What's that? Pi is over here. Or cosine graph would look like this. Cosine of pi would be down there, -1. So -2 minus root 3, that's definitely negative plus negative. And then 2 pi, cosine of 2 pi is the same as cosine of 0. That's 1. So that's going to be the same first. So there it is. So that number line, remember, tells me everything I need to know about f, whether it relates to increasing, it's increasing from 0 to pi 6. It's increasing from 11 pi 6 to 2 pi, right? Our endpoints. It's decreasing in here if I needed that. Where's the local max? Pi over 6, and that's the one we have to give the long explanation, right? We have to say the local max is at pi 6 because G prime is going positive to negative, so G is going increasing to decreasing. Or the local min, same type of explanation. So make sure we do that. Yes?
Can you plug the pi 6 and 11 pi 6 back into?
I plug these numbers in between.
Oh, yeah.
back into. Because if I plug these numbers, you just get 0, because that's what you saw. And so you may try that, and then you get 0 and go, oh, yeah, I'm stupid. All right. And that's it for the G prime number lines. That'd be local max, local min, increasing, decreasing, that kind of stuff. And then we needed inflection points, right? Or maybe the question just asked about concavity or whatever, but that means F double prime. So we go to our second derivative. Now, for whatever reason, I picked several of them that we've done here. The second derivative ended up being sine. And where does sine equal 0? Well, at those 3, but 2 of them are the endpoints, so we don't want to count those, okay, as inflection points, because we can't look on either side, all right? But it could have been cosine. There's no reason to have cosine here, so then we'd have got like pi halves and 2 pi halves. So then there might be more than one inflection point. But anyway, so we get rid of the pi. So that's happened to us before. So we pick a couple values here, plug them back into G double prime. So pi halves, sine pi halves is 1 times negative 2. 3 pi halves, sine is negative 1 times negative 2 pi. So this tells us all about concavity, because it's G double prime. So G be concave down from 0 to pi, G be concave up from pi to 2 pi. But they want an inflection point. So is that an inflection point? Yes, because it changes concavity. This is the one, again, you give a long explanation. X equals pi is an inflection point because G double prime goes negative to positive, so G goes decreasing to increase. Excuse me, concave down to concave up. Okay? Yes, right. In this problem, they're my endpoints. And so if I would have put them in here, we just don't look on the other side of endpoints. In other words, so just as a general rule, local max, local min, and inflection points will not be at the endpoint. If you put them in, I would not count it wrong. If you didn't think of that and you did the 0, 2 pi, did the whole interval and said I had inflection points at all 3, I would be fine. Yes.
You still put them in, find if it's negative or positive,
Well, that would be a problem because if you put 0 in here and you put it in here, you get 0. You get what I'm saying? I mean, you want the positive or negative, so that's why I picked pi halves, 3 pi halves. Because if I would have picked 0 or 2 pi to plug in, then that would have been a problem. So sometimes you don't think of that, and you put them down on your number line, and I'll just ignore them.
And that's not for every G double prime.
That doesn't always happen.
It's just this case.
Just in this one. Right. Okay? Now let's look at number 45. This is the calculator one. Okay, and let's see, Matt, I think I have you up as the presenter here. Yes. Okay, so go to your, there you go. Go to your calculator screen and go ahead and do the derivative here. Now, so everybody's going to need to know, like we did yesterday, the derivative on the calculator. Well, you won't have to because you should be able to do it by hand, but you're going to have to know the solve part and the part where we plug the values in for our number lines on the calculator. So you could do this derivative by hand, right? And this is a problem that's asking about local max min and inflection points. So that means we need F prime and we need F double prime. So I went ahead and did F prime by hand. Matt, are you doing it? Yeah, Matt's doing it here. Now, he picked, that's interesting, you picked, go ahead and keep going. Whoops, you got to close that parenthesis, that plus sign there. Yeah, you've got the plus inside the parenthesis. Just, yeah, there you go. Now, while he's finishing that, notice he picked a derivative one that has this box there. And there's one that doesn't have that box there, right? This one, actually, you could do a second derivative if you put a 2 in there. If you put a 2 in that box, it'll do the, but usually we do that. We need the first derivative first anyway, so we just do the derivative of the original, and then we do the derivative of the derivative. Okay, so there's his first derivative. And since we're going to do inflection points on this one anyway, we know we're going to need the second derivative, so I'd say go ahead and do the derivative again. So go ahead and grab your, well, first you better arrow back down there. You better grab your derivative template. Okay, so you grab this one, but that one up, the one up on the other row could have been used as well. Okay. Now just arrow into that box. Now arrow up and grab that, and then hit it again. Okay, so there's his second derivative. Yes, question.
Is it okay if I ask questions on all this?
Yeah.
Like the timeline? Remember when we were talking about like the timeline when you get positive,
Yeah,
is it possible that all of them are positive?
yeah. And so then it just depends what it is you're looking at. If you have a double, remember this is concavity, second derivative.
Yeah.
So these are all positive. It means the graph's always concave up. Concave up stays concave up. So there's no inflection point because it didn't change concavity.
Well, when I was on the F prime.
Okay? So if you're on the F prime graph and these are all positive, it's never decreasing. It's always increasing. So if this is positive, 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 then the graph's always increasing, which means you don't have any, it would be flat. You'd have stationary points, but it'd be increase, flat, increase, flat, increase. Okay? And there'd be no local max, local min. But this one shouldn't have come out that way.
I was doing 37 over a year, but then why I still got like zeros and stuff.
That's fine. You can have zeros. Remember, stationary points means where it's flat. So it can go up,
Those aren't going
flat, and then go up. So if you have positive, 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 whichever flat spots there. So they're not
Okay.
local max or local min. But on these examples, since these are sine and cosine, they always do this. They don't have flat spots, you know. Well, maybe something didn't go right. I don't know. We'll look at that. All right. So now we need to solve. Now we need to set the first derivative equal to 0 and solve. Okay, so go to menu and algebra and solve. And I just want to make sure we may not have time to finish this whole thing. But we do that, so we grab the derivative, set it equal to 0, comma, x, and then where do we put the vertical bar? Outside of everything. Just one vertical bar. And where's the vertical bar? It's in the equal sign there. And now we put our restriction where we go 0. What is this one? 0 to 5. So we go 0 less than or equal to, there you go. Less than or equal to x, less than or equal to 5. Oops, you gotta have an x in there. And then less than or equal to again. And then 5. And hit enter. A lot of times you want to hit control enter to get decimals. And we get like 4 of them, I think, right? Let me read them to me. We get 0, which is one of our endpoints, but we'll go ahead and put it on there. Say, and we'll go 3 decimal places. 3.142. What's the other one? 189. Yeah. Is that what they were? Okay. So you just arrow up here and you scroll across and you read them. It is pi. This one's actually 2 pi thirds, and I think the other one is 4 pi thirds. I'm not quite sure why it didn't give us to them as exact answers. Usually it can find those when they're exact answers. But anyway, that's fine. Calculator 1, decimals are fine, as long as you got 3 good decimal places. Okay, now we need to put those on our number line. Okay, so we got these values here, and we got 4.189. And we need to plug these, not these, but we need to now plug stuff that's in between. Now 0 is my endpoint, so I don't really need to go on this side of it. But I need a 1, and let's see, what would go to here? 3, 4, and 5. So I need a 1, 3, 4, and 5 to get plugged into my F prime. So, yeah, this is where we talked about the curly bracket thing. So yeah, delete that. Well, you don't want the solve now, remember. We don't want solve here. So I would just, yeah, okay, you can delete that out of there. Or you could have just went up and grabbed your derivative up here. But remember, when we're plugging values into our F prime, that's not solving anything. It's evaluating the expression. So we're taking, and we take out the comma x and the equal 0. We don't need any of that. We don't need the parentheses. I mean, they could be there, I guess. Okay, that's fine. That's fine. And now we have our vertical bar. So we've got our expression for F prime. Now, if this confuses you, you're perfectly fine to put a 1 in each of those and get it. Then put a 3 in each of the x's, get it? Put a 4 in each of the x's, get it? But what did we say yesterday we could do? X equals, and we could go x equals 1 and do it, x equals 3, do it, x equals 4, or curly brackets, 1, comma, 3, comma, 4, comma, 5. We needed like 4 things, didn't we? Okay? So we could do the curly bracket to put all of them in at once. You mean 4.5? Wait. So 1 would be in here, 3 would be in here, 4 would be in here, and 5 would be out there. Okay? So we go ahead and we do that, and we get what? Oh, you hit control it. You're going to hit control it. Well, you have to hit there, control it. There you go. So we get a negative, then we get a positive, scroll over, then we get a negative, then a positive. So again, it doesn't always happen that way, but this does. So a negative, positive, negative, positive. So there's what? 1, 2 local minimums. There's a local max right there, right? You have to write out those explanations, all that good stuff. Where is it increasing? It's increasing in between here and here, from here to 5, right? Where's it decreasing? So all that F prime stuff is there. All right, and then for the second derivative, be the same business. Okay, we won't take the time to go into that. But so second derivative, we already had it. Set it equal to 0. Do a solve. Set the restriction from 0 to 5. Get those values. Those are possible inflection points because it's a second derivative we're doing now. Put those on the number line. Pick numbers in between. Tells you when it's concave up, concave down. If it changes, then you've got inflection points. And that's it. I mean, really, this was a pretty good going over of the whole ball of wax. I mean, if you can do, I mean, we talked about a lot of different things today, which a lot of them were things we talked about yesterday too. Okay, but hopefully it's getting a little clearer, a little better. Okay, like I said, and I don't know who came in late here, Natalie. I said I'm going to be up here at the school at 4 o'clock on Sunday for anybody that wants to come up for review, whatever. Okay, ask questions or anything. So, and don't forget about the these videos on these review videos. The one under 2.4 to 2.7 are just some of these local max, global max, min, inflection point. Okay, not to mention that I recorded today's lesson as well. So all the stuff we talked about today for you guys that came in late is up there. So. A lot of opportunities to get these things here. All right, so quiz will be Monday. Oh, and you guys that came in late too, John and Natalie, I've written up here that the next group of 3 would be just some more review problems. I singled out some of the review questions at the bottom of the assignment sheet that have more to do with our quiz than others. So instead of doing that whole line of review problems, here are some that might have to do with the quiz more. Okay, it's not necessarily a full review, but I mean that's some of those things. And then on 2.4, we said that was global max min problems, but those were more polynomials, like where it was just factoring and foiling stuff. And so you can get some practice on those. They're probably easier than the trig ones, but they're the same. Yes. Yes.